Hello and welcome back to Pre-Calculus. On the menu for today, section 2.6 on rational functions and their graphs. Now, we have seen a basic rational function, which is 1 over x, and today we're going to dig deeper into the rational functions and everything those functions bring us. Now, before we do anything about rational functions, we should define what rational functions are, and then start going through the examples. So, rational function is a quotient of two polynomials. That's it. Generally, we would say r of x equals p of x divided by q of x, where q of x is not allowed to be 0. Now, the fact that q of x is 0 in some cases will bring other headaches that we have to deal with as we go through. They're good headaches, but those are very important headaches, as we are going to see. Okay, so to start the story here, we are going to look at the basic case of 1 over x, when you take a constant polynomial 1 and you divide it by the linear polynomial x. So, f of x equal 1 over x. Now I'm going to draw the graph for this, and this graph will be used so much in calculus to explain a lot of different concepts. So you really must learn this graph. No doubt about it. Now we are immediately going to notice that there are no x or y intercepts. We will also note that that the domain is from negative infinity to 0, and then it's interrupted, and then 0 to infinity. And we also see that the range looks the same. Negative infinity to 0, union 0 to infinity. We also see that these parts of the graph are all decreasing, not so important for your pre-calculus class, extremely important for calculus later on, but it's decreasing, meaning that if you are to walk on this line towards the right, you would be going downwards down the line, and you do get to do that on both of these parts. Other stuff, no min and max, there is a symmetry to it and so on, but we don't have to worry about all of those gory details, as they will be later on worked on in calculus. But at least this much, right, what's displayed is to see, is for you to know, I mean. And technically all of it is just, you look at the graph that you memorized and learned, and you come up with all of these things. So you don't have to memorize the domain and range. You can just look at the graph and say, okay, what are all the x values that I have the function for? And then what are all the y values that I have the function for? And those are all listed right there. The next is going to be a modification. Let's say you have 4 over x plus 3. Now, what do these numbers do, right? Because we know we are comparing this to 1 over x with the vanilla picture like this, right? So the question is, how does the problem that I gave you here, how does that differ than 1 over x? I.e., what transformations do I have there?
Would it be a shift?
Okay, keep talking.
To the right? To the left?
Mm-hmm. So
by 3.
Left 3, good. And what is this 4 up there?
So would that be a stretch?
Yes, very good. Vertical stretch. Now, we can't really draw that, so we kind of ignore it. But yeah, that's a vertical stretch times 4. Times 4. There we go.
When we're like tested on this, would we be ignoring the vertical stretch too? Or is there
Yes,
going to be like, okay.
you will be ignoring it because you can't really. I mean, you could, but it's just too much. All right. So we're moving left 3 units. It seems as if there is some kind of guideline on the y-axis that the function was following. And now I move that guideline 3 units left. And then I draw my function. Okay. That was not terrible. All right. So I hope you see that there is this guideline right here and another guideline right there that the function kind of bends and follow into infinities. Do we see them? Anyone? These red guidelines, how the black pieces of the function are trying to follow these red lines?
Yes.
Okay. Whew. So now, note that with my shift to the left, that guideline I had at as a y-axis shifted 3 units to the left and the graph still follows it. I can do that also for the x-axis guideline. So let's say you have the function, let's use f of x. F of x equals to 3 over x plus 2. So what is this plus 2 now going to do here?
Move it up 2.
Yep, very good. So this guideline moves up and our graph will go like that. So you always start with your vanilla 1 over x and then move it where you need to move it. So here's a problem for you guys to practice. Doesn't matter. So try this one. No pressure. You have 18 seconds. Go.
I think I got it. I don't know if the 18 seconds are right.
All right, I will draw, and then you can compare. Now, can you share your transformations?
I got left 2, down 3.
I
Oh,
will
wait.
agree with
I just
down
realized.
3.
Yeah, never mind. Right 2, down
Mm-hmm.
3, vertical stretch by 6.
Yes. So right 2. All right. So now I'm going to draw the axis. I'm going to go 2 units to the right with the guideline. And I'm going to go 3 units down. And now that acts as a new coordinate system technically for me to draw the function. So if you have something like this in your notes, now this 6 is a vertical stretch, yes, we all understand and know that, but unfortunately we can't really do a great job there right now on a paper. So we just leave it. Sweep it under the rug like it doesn't exist, you know. So I hope you have seen that we just used 1.6, right? Shift left, shift right, up and down. We can also reflect. That's fine as well. We haven't done any of the reflection problems. So let's just do one more and then go into the spicier situations. So how about -3 over x plus 4? So let's see what you get for that. I'll give you some time and then kick in. All right, let's take a look at this together. So we have a a flip, right? Is it an x-axis or a y-axis flip? This negative. I guess you forgot 1.6 by now, right?
The
That's what.
negative isn't a horizontal stretch?
Well, I'm asking for a flip with a negative. Is it on x-axis or a y-axis?
Wait, the x-axis is if it's not directly on the x, right?
Yes.
The negative. So it would be the y-axis.
No, the x-axis.
What?
Yeah,
Wait.
because you have this situation. That's the x flip. And when you have this situation,
Oh,
that's a
okay.
y flip.
Whoops.
So it's a minus on the entire, see? Minus on the entire problem, which means that we have x flip. Okay, so we have x flip, and what is the 4 doing?
To left.
Yes, 4 left. Good. So we are going to, oops. We are going to move 4 to the left and flip on x-axis. So 4 to the left, 1, 2, 3, 4. So our guideline now becomes this line. And since we have to flip, it's going to go there and here. Now, since we did not move it up or down, you're still having the x-axis to be the guideline. So I have been avoiding the true word that we have to learn today. I use the word guideline, but it's not called guideline. It's called an asymptote. We have a vertical asymptote, and then the horizontal guideline, which I had before, called horizontal asymptote. So those are mathematical terms that you need to learn now. All right. Now, these two will be fully explained and defined in calculus. Now we're going to have some vague definition of them. Just enough so we can use it. That's it. But the calculus will give you the real deal. So, the vertical asymptote known as VA is a vertical line which function cannot cross instead f of x follows VA to positive or negative infinity. Um, the location is determined by solving the equation. Well, let's just put q of x because we know q of x equals 0 after canceling all factors from P of x and Q of x. All right, so let's talk about this. Vertical asymptote is a vertical line, so it will have some equation x equals a number. We know that from algebra. So vertical line, right? And the function has to follow that line into infinity. It can't cross it. So you want to think about yourself and a wall. You can't go through a wall. Let's say it's a brick wall, because these cardboard walls we have, I can at least go through them. I did in the past, which was a lot of fun. But let's say you have a brick wall or a real concrete wall. You can't go through it, right? So if you want to think about a vertical asymptote like a concrete wall, good. And then you can just climb up to that wall forever and go down that wall forever, but you can't go through it. Now, you get the x equals whatever number it is for it, right? You get it when you set the denominator equal to 0. But that is not the full story. You have to cancel expressions, otherwise you're going to get what I call a false positive, meaning you compute the values for asymptote, and it turns out it's not an asymptote. And the reason why is because that term would actually cancel, but you haven't canceled, let's say, and then that's why you're getting the wrong answer. So let's first take a look at a simple example. F of x equals 3 over x plus 6. Okay. X plus 6 equals 0. X equals negative 6. Vertical asymptote at x equals negative 6. Good. And we're done. Now, there was nothing to cancel between the numerator and denominator, so we have our one asymptote there. And you can go and graph. F of x equals x plus 6 divided by x squared plus 3x plus 2. Okay, you see that you can factor the denominator, so factor it as x plus 2, x plus 1. Still nothing cancels. So when you set your denominator equal to 0, by the zero product rule, you get each one of these equal to 0. So x is negative 2 and x is negative 1. So now I have two vertical asymptotes. VAs at x equals negative 2, x equals negative 1. I have two of them. You will learn later on that 4 out of 6 trigonometric functions have infinitely many vertical asymptotes. Just give me a month, okay? Just give me 1 month in this class, and we're going to say that tangent x, right, trigonometric function, has infinitely many vertical asymptotes. So this business with vertical asymptotes, right, doesn't start and end here. It is something that you will be dragging with you forever while you're taking math courses, or I'll show how this concerns the design of things as well. So that's your working career. Now, why is this canceling business important? Well, let's take a look at this. You see, if you set up your denominator equal to 0, you're going to get two numbers, positive 5 and negative 5. And, one of them has to be thrown out. So that's why you first factor and cancel, and then that simplified result might or might not have an asymptote. So we go x plus 5 over x minus 5, x plus 5. See, I can factor that. And now these guys cancel. So my simplified version of the problem is this. And as you can see, there's only one asymptote at x equals to 5. Just one asymptote. And if you graph this function on your graphing utility, right, you will see that there is only one asymptote. So the graph will look like this. I will show you the graph. I don't want you to be disappointed or something. So x equals 5. Hold on, tablet. Relax. Relax. Thank you. 1, 2, 3, 4, 5 is the vertical asymptote. And then you have the negative 5 on the other side, which is not an asymptote, but it's the open circle. And that is, let me see. So these guys cancel. When I have negative 5, it's going to be a negative 10, so it's going to be here. 1, 2, 3, 4, negative 5, so it's going to be somewhere over here. So your graph should look like this. Right? Because the other one is a negative 5, those cancel. Yeah, it's 1 over negative. I mean, yeah, 1 over negative 10, which is negative 1, 10. Okay. So this is what the graph would look like. So if you just find your vertical asymptotes right here, you would get positive and negative 5. But we just seen that negative 5 does not have this guideline. So the function is just an open circle there because you can't have that value still. In the original function, you can't plug positive or negative 5. But the negative 5 turned out that it's not an asymptote. It is what we call here an open circle, right? So it's just a value is missing there. Your calculator will return on these the error, right? If you're using the TI-83, 84, whatever, it returns error in the table of values at both of those locations. So calculator cannot really distinguish very well between the open circle and the vertical asymptotes. I mean, unless you graph it, then you see this graph and you know there is only one asymptote. So to sum up our vertical asymptotes, what we have here is the vertical line, which is like this guideline that the graph is going to follow. And that line is infinite, going up forever and down forever, which is why the functions follow it forever up and forever down. That line cannot be crossed at any point by a function. And the function bends, right, to follow it, and it does so going to infinity. So to find vertical asymptotes, you will set the denominator, the q of x, you will set the denominator equal to 0. But you only do that after you do necessary cancellations. Because in some cases, your cancellations are not going to have, right, the same values. So your calculation for asymptote, right, when you set the denominator equal to 0, sometimes it's not going to have only asymptotes show up there if you didn't cancel prior to that calculation. So which is why, as you can see in this particular example, I canceled first, and then I regarded 1 over x minus 5 as a completely new problem, which you can say, oh, shift to the right 5 units and then draw the line there. So this is a vertical asymptote at 5, and in this case, just the open circle for negative 5. So that's the vertical asymptote. And vertical asymptotes show up when you have 0 in the denominator or when the function value is missing, which are both, in many cases of application, catastrophic events, actually. So anytime the piece of technology explodes, right, and quite a number of companies had their devices, the batteries, explode and so on, or pop, there was some denominator somewhere that was overlooked in the calculations to build that. So there are a number of examples. I don't want to waste time on it now. And now we're going to take a look at horizontal asymptotes. Usually I put horizontal asymptotes blue. So horizontal asymptotes in this particular class for rational functions is going to be determined using the three rules that you memorize, and then in calculus, when you get the real definitions and so on, you can forget them. But you will need them to survive Precalc 1 and, I mean, the whole pre-calculus course sequence. Abbreviated as HA. So HA is a horizontal line, y equals to some number, that f of x has to follow as it goes to positive or negative infinity. Ha can be crossed by a graph locally, but not at positive and negative infinity, because it has to obey the asymptote in infinities. Now, the rules, because you guys don't have the concept of something called limit from calculus, so you will have to deal with rules. 3 rules to help you. Given f of x equal to, let's say, a x to the m divided b x to the n. So these are the leading terms. Right, one with the highest exponent. We don't care about the other ones. If m bigger than n, no ha. 2. If m equal n, ha at y equals a over b. 3. If m smaller than n, ha at y equal to 0. So these are the 3 rules that you have to memorize and use them for horizontal asymptotes for rational functions until you hit calculus, where we give you the formula for all functions. And in that case, right, when you have all functions, you have this. All right. So now that we have this rule, let's take a look at a couple of examples real quick to match them to this. We'll start with the good old friend 1 over x. So exponent on top is 0, right? Because x to the 0 is 1. And an exponent on the bottom is 1. So you have the situation that denominator has the bigger exponent. So in this case, m is smaller than n. Therefore, horizontal asymptote at y equals 0. Y equals 3x squared plus 6x minus 4 divided by x squared plus 1. Well, your leading coefficients are 3x squared divided by x squared. Exponents are the same. So if exponents are the same, then y equals, actually, horizontal asymptote at y equals 3 divided by 1 is 3. We learned, right, that you are supposed to divide those leading term coefficients. So 3 divided by 1 is 3. It's very simple to use this, but you have to remember the rules. So when denominator has the bigger power, asymptote is always 0. When numerator gets a big power, then there is no asymptote whatsoever. And if they're the same, just take the front coefficients, right, the leading term coefficients, and divide them. And that's your asymptote. Now, there is one more type of asymptote that we need to add to this list, and it's called the slant asymptote, which is actually offshoot of this one. And this one happens if m equals n plus 1. If the top, right, the numerator, has 1 degree power, like 1 higher than the denominator, then you have a slant asymptote. And the slant asymptote is the asymptote that functions follow, but that asymptote is not horizontal or vertical, it's at any angle, right? Because it's y equals mx plus b that governs that line. So slant asymptote
It was
sa.
m equals n plus 1, right?
Yeah, I'm going to write it again. Slant asymptote here is so slant asymptote is an asymptote of the form y equal mx plus b. F of x has to follow it at positive negative infinity. That means locally it can be crossed, but I don't think you have a single example in a pre-calc. In calculus you are going to run into it, but I don't think in pre-calc you have any examples of that. Okay. We have sa when m equals n plus 1. The degree of the numerator is by 1 larger than the degree of the denominator. And finally, the icing on the cake, as this was not enough information, we compute sa by long division of polynomials. And here, the smiley face to kind of make this a little bit less threatening. we have 3 different types of asymptotes. Oh, maybe it's worth also mentioning that ha and sa cannot occur in the same f of x. They're what you would call mutually exclusive. So if you have one, you cannot have the other. You can have neither, that's fine, but you can never have both of them, right? So it's one or the other or neither of them, but you can't have both of them. All right. So now let's take a look at an example which would have slant asymptote. So f of x equals 3x cubed plus 6x squared minus 3 minus, not 3, minus 4, because I don't want it to, so you can factor it, right? So just 4 there. And then denominator is, let's say, x squared minus 1. Great. So you go and say, okay, vertical asymptotes, since we can, right? It's going to be x squared minus 1 equals 0, x equals plus minus 1, and I don't think any of them cancel, because you can go and check if plus and minus 1 using synthetic division, if they are roots of this, because if they are roots, then they would cancel, in which case you don't have vertical asymptotes there. Terms which cancel inside the function do not have vertical asymptote at that location. So we check one in 3604. That's a 3. That's a 9. That's a 9. That's a 9. That's a 9. And that's 13. That's not a 0. And now negative 1. 3604. That's a 3. That's a negative 3. That's a 3. That's a negative 3. That's a negative 3. That's a positive 3. That's a 7. It's not a 0. So it's not divisible. This is not divisible by either x plus 1 or x minus 1, which means they don't cancel. So because they don't cancel, both of these are vertical asymptotes. Good. So remember, you have to cancel first and then find vertical asymptotes. I kind of did it backwards here, where I first found vertical asymptotes and then I checked if they actually are asymptotes. But you have to check, because you've seen this problem, right, where it looks like you have 2 asymptotes, but you actually have 1 because the one canceled. All right, cool. So now going back to this problem, that's the vertical asymptotes. We have 2 of them. Now, for horizontal asymptotes, well, none, because m is bigger than n. All right? And finally, slant asymptotes. Yes, we have that, because you have x to the 3 on top, x to the 2 on the bottom. That's difference by 1, right? And we said m equals n plus 1. So you have your 3 equals 2 plus 1. Okay, cool. There's your 3, there's your 2. So it fits, which means that we can do long division of polynomials to figure out what the equation for it is. So x squared plus 0x minus 1. Remember, I'm putting a placeholders here. Plus 0x minus 4. And now we do long division polynomials. X squared goes into 3x cubed 3x times. Multiplied back, you get 3x cubed plus 0x squared minus 3x. You see how well these placeholders work? Because this would be a like whole mess if we didn't have them. These guys cancel. You got your 6x squared plus 3x and then minus 4. It is this minus and the minus in front that makes a plus 3x. Now x squared goes into 6x squared plus 6. We're done. I don't care about remainder. I don't care about anything else. because we were hunting for y equal mx plus b, and you got it. So it's always this short, regardless of what exponents you have. So we are able to now find the slant asymptote, right? So slant asymptote at, and then you give the equation. So now all of these give you the guidelines on how to draw the function, which drawing the function, sketching the function here, right, is something that we are trying to learn. So we have our -1 and 1 vertical asymptotes. And then we go to 6. 1, 2, 3, 4, 5, 6. And then go 3 up, 1 over. You can also go 3 down. 2, 3, 1 over. And 1, 2, 3, 1 over. So here is your slant asymptote. Right, that's the slant asymptote. And then the function is going to do something, right, in between these lines. Now, we're not there yet, so I don't want to go through the ways of graphing them. But now, since we are talking and learning about asymptotes, it's good to graph those and see. And there are no horizontal asymptotes for me to put any lines like this anywhere, because there are no horizontal asymptotes. So these asymptotes are guidelines, right? And your function is going to follow them. Now we'll see which way that happens. All right, cool. So there we go. So for now, we know the rational function definition, right? Division of two polynomials. We know that we can deal with the 1 over x quite easily because we know enough algebra. And we know also some of the 1.6 shifts, so we're good there. The problem now that we have is that these guidelines, right, are 3 different types of guidelines, which we call asymptotes. The problem is that, right, they all have their own rules, and you have to remember them all. So, again, vertical asymptote, once you are done with all of your cancellations, you go and set denominator equal to 0, and that should spit out the x values at which you have vertical asymptote. For horizontal asymptote, you must memorize those 3 rules. And the slant asymptote is the offshoot of number 1, right? Because the numerator has the bigger power by 1, and every time when you divide them, right, since they're off by 1, it will always produce the linear line, which would be our slant asymptote. So now when someone says find asymptotes of f of x, you have 3 different kinds of asymptotes to worry about: vertical, horizontal, and slant. And that's not going away, right? We have to do 100% of this in calculus chapter 4, graphing functions by hand. Right, over here we are kind of scratching the surface a little bit to set up some really cool stuff later on. I also see, oh, okay. All right, so now, if we want to graph these rational functions, we need to be able to find enough information so that we can graph this on the paper. The way we do this is, as I like to call it, we make a shopping list of things, which are the intercepts and the domain and the asymptotes, right, and additional points if we need them. And then we use all of that information to draw a graph. So that's going to be the next. Oh, I forgot to talk about the end behavior. Hold on. That just popped into my head. Let's go green. Like this is the least threatening of everything you have seen in this section, because it simply tells you which way the function goes as you graph it. And you already had the end behavior for polynomial, but they all went to infinities. End behavior for this one can also be the horizontal asymptote, which turns into a number, right? So end behavior from before stays in one of the 4 cases like this, right? And it simply means that the function is going forever up, right? So that's going to be a positive infinity up and positive infinity to the right. And here's the other companion on the other side, positive infinity up and negative infinity to the left. What function has that behavior? X squared function, right? If I have f of x equal x squared and you graph that, whoop, you can see that these two, right, the middle one is the y and this one is x, but the parabola actually, right, this one is going forever up and it's going forever to the right. On the other side, it goes forever up and forever to the left, right? So end behavior just shows you which way the function would go forever, right? And kind of generally, the interesting things happen in the middle of the function. Nothing ever exciting happens at the end of the function, because that function just goes to infinity in the same fashion, forever and ever and ever and ever and ever. All right, so that's just a little bit of this end behavior which could help, but again, it's not guaranteed, because some of the functions are going to follow the asymptotes, the horizontal asymptotes. So in that case, it's not going to go into infinities. So now I just want to go through and graph a couple of these using what I call, maybe I should write that, the shopping list. So using the shopping list. This is not the shopping list, okay? This is not something that you will find in the book. It's my creation. Number 1, we want domain. Number 2, we want x and y intercepts. And you get those when you set y equal to 0, you set x equal to 0. 3, we want the vertical asymptotes. 4, horizontal asymptote. 5, slant asymptote. Right? So all of those are important to us. And then 6, maybe additional points. Let's take a look at the example immediately and see all of these, the entire shopping list. See it at work. So let's start with problem 60. F of x equals 4x minus x squared. Over x squared minus 1. There we go. Perfect. So what do we have in this? What do we have in this case? Well, we start with domain. Well, domain is going to be interrupted by vertical asymptotes if you have any. So we can leave the domain open and fill it in with the vertical asymptotes. Or you can just say, well, domain is going to be all of the points minus the bad points, which is where the vertical asymptotes are. What I call the bad point is the point singularity. It's the point where your function has 0 in denominator, and that's not good, which is why you have a vertical asymptote there. And you also have interruption in the domain because you can't plug those values in the function because they have 0 in denominator. So it's a vicious cycle there. If I do this, and then I ship 1 to the other side, and then square root both sides, which will give me plus minus 1, I will find plus minus 1 as vertical asymptotes. Again, because the factors that you get here, x minus 1 and x plus 1, they don't cancel with 4x in any way. So now we have that there are two vertical asymptotes, right? A vertical asymptote at x equals minus 1 and vertical asymptote at x equals positive 1. That makes break in our domain along those values. We just write it out. So when you want, if you have a polynomial, right, like let's say 4x, it has all real numbers as the domain. And then you have to chop it up with this particular denominator, right, which could be 0 at 1 and negative 1, which is why we have this. We have still negative infinity to positive infinity in our interval, but we also have two interruptions, which are where the asymptotes where the asymptotes are. So when I draw this function later on, this function is going to have three pieces because the spacing cut by two asymptotes into three separate regions. All right, let's go with 2 and 3, and then we'll figure out. So x-intercept, set y equal to 0. Okay, that's easy. 4x over x squared minus 1 equal to 0. Cross multiply everything, you get 4x equal to 0, and you get x equals 0. So your x-intercept and your y-intercept is, in this case, 0, 0. Okay, we got our x and y-intercept, right? Because 0 here, that means it's also y-intercept at the same time. You can't have more than one y-intercept, so we are not going to waste time to look for y-intercepts because you already know that you have a 0, 0, right? So 0 on y is the intercept, and then you are not allowed to have another one. Okay. Number 3, vertical asymptotes. Oh yeah, we got that. Vertical asymptotes, that's x equals negative 1 and x equals 1. So that's important information that will be graphed. So let's box it up. 4. Horizontal asymptote. Do we have them? Yeah. You see, the denominator has a bigger power. So y equals 0, which is technically x-axis, is our horizontal asymptote. Now, because you have horizontal, you cannot have slant. So SA is none. No slant asymptotes. Again, just because you had the horizontal, then you can't have slant. All right, cool. That's that. And when I say maybe additional points, we're going to hold off on it until we see how much of the graph we can actually draw. So I have my y equals 0 and my vertical asymptotes at negative 1 and 1. You know what? I'm going to just make it. Actually, how about we make the red? There we go. The red ones was what I used for vertical asymptotes, and then blue is going to be used for horizontal asymptote, which is at 0. There we go. Remember how you have x and y intercept at 0, 0? Yeah, that one is going to cut through the horizontal asymptote. And that's what I said. Horizontal asymptotes can be crossed, but locally. They have to be obeyed at infinities, right? But locally they can cross, a function can cross through the asymptote. Horizontal asymptote, not the vertical. Vertical can never be crossed anywhere. Okay. I placed down all of the information that I had on this graph. I have the 3 asymptotes, 2 vertical, 1 horizontal, and I have this xy intercept at the origin. I don't have any more info. Like, that's it. So now what? Well, now we're going to use a little bit of common sense to fill these parts. So let's start all the way on the left. I'm going to use the green color here to draw 2 possibilities. These are the only 2 possibilities that you can have to the left of -1. You can't have anything else. It has to follow the red and blue asymptote into infinities. So it could be either going up or going down below. It can't start somewhere and cross because we did not find any extra x-intercepts. So it will not cross the x-axis at any point. So I can't come up with something like this or whatever, because right, they have to be contained and they have to follow. So it's one of the 2 green lines. So one I have to delete. You can't leave both of them because it's no longer a function. It fails vertical line test. So you have 0 for the problem because the problem says graph a function, and then you put the 2 green lines one on top of the other. Well, it's not a function anymore because it fails vertical line test, and it's 0 for the problem because the problem says graph a function and you graph the non-function. So you have to remove one of these 2. Now, which one do you remove? Do you remove one on the top or one on the bottom? And this is where the additional point calculation comes in. See, you have your function 4x over x squared minus 1. Right? That's our function. I can pick -2. And that -2 will give me negative y value or a positive y value when I compute. So I'm literally computing f of -2 here. That's 4 times -2 divided by -2 squared minus 1. That's -8 divided by 4 minus 1 is 3. So -8/3. That's that one. So I erase the top and kind of make this one. Now we can repeat the same thing on the other side. Because middle is tougher. So we're going to do that last. Middle has more combinations. So now you are faced with the same dilemma. Do I leave the upper one or the bottom one? And clearly, you will compute a single point at 2. Okay, that's f of 2. That's 4 times 2. 2 squared minus 1. That's 8/3. Aha. 8/3 is a positive, so I get to keep the top one and kill the bottom one. 2/3 of my graph is done. I just need to figure out the middle. Now, the middle is very tricky, guys, because you can have a lot of combinations here. Look at this. This could be a thing. Or the other way. Or it could be parabola just going like that. Could be parabola going like that. So there are many combinations. The interesting thing is that all of them have this behavior. They emerge from the black point and they have to follow the red line. They don't care about the blue. Right? Locally, we said they don't care about the blue. So when you have this, you say, oh, well, this is actually the same problem, except now I have to compute at 1/2. See, you compute at negative 1/2, and you compute at positive 1/2, because that's going to give you either positive or negative value, and then you erase the other line. So it's kind of harder to see that, just because there are so many of these combinations. But it's the same deal like we had here. You plugged in -2 and you got a negative number, so it's the bottom line. You plug in +2, we got a positive number, so it's the top line. So now we're plugging in a half or -1/2, and then that's going to give us positive or negative number. We keep, right, whatever we get. So f of -1/2 is going to be 4 times -1/2 divided by -1/2 squared minus 1. So on the top, half of 4 is 2, so -2, divided by, and this becomes 1/4 minus 1. That's also negative value. I actually don't care what the value is. I just want to know if it's positive or negative. And look what I have. I have a negative number divided by a negative number. I don't care what this is. It's just smaller than 0, right? So it's sorry, it's larger than 0. It's positive. Negative divided by negative is positive. So you can go and compute exactly what the value is, but no one cares. I see a negative number divided by another negative number. Negative divided by negative is positive, which means that for -1/2, I'm keeping the upper green line, this one, and I'm erasing the bottom one. Do this calculation one more time for +1/2, and we're done. 1/2 squared minus 1. So now you have a 2 on top, and still 1/4 minus 1 on the bottom. This is positive divided by a negative gives you a negative. So now we keep the bottom line and erase the top. There we go. And there's your graph. 30 minutes later. There's your graph. That was problem 60. You have like 30 of these exercises. So let's take a look at another one, because we can. I think 79 looks disgusting enough. I mean, beautiful. That's 3x squared plus x minus 4 divided by 2x squared minus 5x. Okay, perfect. Let's cry. The first order of business is always factor everything, see if anything cancels. Because if it does, you're going to have less vertical asymptotes. You know, in all honesty, I don't like problems when they cancel, because I have less stuff to work for. I mean, less stuff to work with to draw the graph. I love having a lot of information, but stuff sometimes cancels, and then you have less information, and you have to figure it out still, so whatever. Let's try and factor the top. Factors of -12, 1 and 12, 2 and 6, 3 and 4. So it seems that I can break it. Oh no, I need -12. I need -12 and +1. Oh, yeah. Negative 12 and positive 1. Negative 3 over here. Good. So we have 3x squared minus 3x plus 4x, see? And then minus 4. That's good. So when I factor out 3x, I'm left with x minus 1. And when I factor positive 4, I'm left with x minus 1. So x minus 1, 3x plus 4. So that's the top. When you factor the bottom, it's a basic GCF, greatest common factor. You just get 2x minus 5. These guys don't have any factors in common, which means that nothing cancels. Therefore, we can start with our domain, right? We have x equals 0 and 2x minus 5 equals 0. So 2x equals 5, x equals 5 over 2. So I have two vertical asymptotes actually, and they are vertical asymptotes because nothing was canceling. And I can write the domain negative infinity to 0, union 0 to 5 halves, union 5 halves to infinity. There we go. You can see that, right, domain is interrupted exactly where the vertical asymptotes are. 2, x-intercept set y equal to 0. So the top is x minus 1, 3x plus 4, divided by x. Always use the factored form because it's much easier to compute everything. So when you cross multiply, right, because you need to solve this rational equation that was in your basic algebra course. You cross multiply and you get your x minus 1 times 3x plus 4 equal to 0. And then x minus 1 equal to 0 and 3x plus 4 equal to 0. X equals 1 and x equals negative 4/3. Those are x-intercepts. Perfect. Y-intercept, set x equal to 0. Oh, wait, I can't. Nope. Because remember, there is an asymptote at 0, which means they will make 0 in denominator, so it's bad. So no y-intercept. And that kind of makes sense because you do have a vertical asymptote at x equals 0, which is y-axis. So you can't have an y-intercept if there is an asymptote on it, because remember, your function cannot cross through the asymptote. So no y-intercept. Okay, we're good there. And the next one is asymptotes. So vertical asymptotes, we already know x equals 0 and x equals 5 halves. That's 2.5, that's easy. Horizontal asymptotes. Let's look at the original problem. Yes, they're the same. When they have the same exponent, that means their front coefficients are an asymptote. So 3 halves. And slant asymptote, none, because we have horizontal. Right? You can't have both of them. So either slant or horizontal. Okay, I got some stuff. Let's graph all of this and then see, maybe we have to play the game again with those values, right? Maybe we don't. Depends on what we get. Horizontal asymptote at 3 halves. Okay, that's 1.5. That's your 3/2 horizontal asymptote. Vertical asymptote at y axis. That's your x equals 0. And then another one 5/2. That's 2.5. Good. And I have the x-intercepts as 1 and negative 4/3. 1 and negative 4/3. That's right here. Okay. Well, we don't have to think on the left side, right? Because we have to go through the x-intercept. Come on, tablet. Stop. And we have to follow these asymptotes. So that side is immediately done. The right side is also done. Look what you just think about your options. This is your option number 1 and this is your option number 2. And it's clear which one we have to delete. Can anyone help me? Which one we have to delete because we don't have a particular piece of information that would keep it. So we have to erase it.
The bottom one?
Yes, why?
Because we don't have another x-intercept.
Beautiful. Yes. There is no x-intercept here. So we have to delete this piece. So see, sometimes you don't have to compute those values. It's just, a little bit of common sense would help. And right? Now, again, that is if you draw the two pieces and you see what's happening, right? Because if I am to draw this piece over here, well, I have this x-intercept. This line on top cannot go through that x-intercept. So I have to get rid of it. On the other side, if I draw this piece, I don't have the x-intercept here, so I can't. I have to get rid of it. So it's the one on top. And remember, you are not allowed to leave them because it fails vertical line test and it's a 0 for a problem because you are not getting a function. Perfect. That leaves us only with the middle, right? Now, the middle is still going to be this tricky because we can have that, we can have the top, right? We can have like that. So we might as well draw all 4 and then test. See, number 2 now is included, so you can actually test number 2 and a 1/2 over here. One half. That's it. So now let's see which ones we are erasing, which ones we're keeping, and the problem is done. All right, so what do I have? I have f of x equals 3x squared plus x minus 4. Maybe it's better to use the factored versions. Yeah, factored ones are much better. You can do the sign analysis. X minus 1, 3x plus 4. And x and 2x minus 5. Why are these better? Because you don't actually have to compute. You can just get their signs and then just say, oh, I'm keeping the one on top or one on the bottom. That's why they're much better. Your green line has to go through that black point 1. That black point 1 that you see there is the x-intercept. And Function has to go through it. No debate there. But we just don't know which ways they go. So here we go. Let's go with f of 1/2. Now, that's going to be 1/2 minus 1, 3 times 1/2 plus 4, divided by 1/2, and then 2 times 1/2 minus 5. I am not even going to compute this. The first parenthesis is negative. The second parenthesis is positive. The 1/2 is positive. And over here I have 1 minus 5, which is negative. The whole thing is positive because you have negative, essentially negative divided by negative. I'm not computing this stuff. There's no reason. You can, and you will get a positive number. See, no one cares about the number. We just care about whether it's positive or negative, so I can highlight the positive value here. That's all I care about, and I delete the one on the bottom. And now, rinse and repeat this analysis for number 2, because as you can see over here, number 2 is, you can use 3/2, you can use whatever, but number 2, right, it's a whole number, it's easy to compute. So you have 2 minus 1, 3 times 2 plus 4, and then 2, and then 2 times 2 minus 5. Okay, so 2 minus 1, that's a positive number. 6 plus 4, that's a positive number. A 2 is a positive number. And 4 minus 5 is a negative number. So the whole thing is negative. So we keep the bottom one. When you computed your function, remember, f of x equals y. When you are computing these numbers, you are getting your y values. Y values are negative below x-axis and positive above x-axis, which is why we are computing these, and also why we care about a sign, not about the value. And there is the graph. There's the graph. I know this is a lot of information for one section. We had to talk about rational functions, take a look at the vanilla case 1 over x, then do the shifts from 1.6 for it, talked about domain intercepts and all that stuff, then introduced 3 types of asymptotes with their rules, long division included for slant asymptotes, and then bring the end behavior into the mix as well, right? And when we mush all of this together now with x-intercepts and y-intercept calculations and figuring out asymptotes, on top of that, we need also to do the analysis of a graph. So I know it's a lot, which is why it's going to take hours to sort this in your head, and you should not be doing this in one sitting. So give it, hour or so in one, sort at least asymptotes out. And then the next day or something, try to put the thing, because guys, if you just cram too much of this too fast in your head, it's gonna get mushed and confused, and your brain has no time, right? If you're just gonna sit there for 5 hours, right, and no one is engaged 5 hours to study, so don't, right? Just sit there, one thing at a time, right? Plow through it slowly in chunks. Let me learn about asymptotes only, and then the next day let me figure out the graphing, because asymptotes are guidelines and I have x and y intercepts from algebra. So now put all of those concepts together, and hopefully, right, we can have a graph. So I'm going to do one more example, and that will conclude our chapter 2. You guys will be ready for the discussion on exam and all of that stuff. All right, so let's see what can we find here. Let's try this 85 and see if we can get it done. What do we have? 22 minutes? Oh, actually 12 minutes. It's gonna be tight. Let's see. X squared plus x minus 6 divided by x minus 3. Remember what I'm doing, immediately factoring, because if I can cancel, that will kill some of the vertical asymptotes. So the top factors into x plus 3, x minus 2, and the bottom stays as x minus 3. Okay, nothing cancels. So in this case, since nothing cancels, x minus 3 equals 0, x equals 3 is the vertical asymptote. It didn't cancel, so it's there. And we immediately have our domain interrupted only at 3, because that's the only asymptote we have now, vertical asymptote. X-intercept, set y equal to 0. So that's going to be our problem, x plus 3, x minus 2 over x minus 3 equal to 0. Cross multiply, x minus 3 will die. And x is negative 3 and x is positive 2. So we do have two x-intercepts. That's an important piece of information. Let's highlight it. Y-intercept, which is set x equal to 0. So what do you have? When you set x equal to 0, you can go back to the original problem. That's 0 squared plus 0 minus 6 divided by, easy, tablet, easy, 0 minus 3. So that's negative 6 over negative 3 equals positive 2. So y equal positive 2 is our y-intercept. Vertical asymptote, already done. X equals 3. Yeah, we did that up there. Horizontal asymptote, nope. Because the denominator has the smaller power than the numerator, right? Numerator has the bigger power, so no horizontal asymptote. Slant asymptote, yes! Because the numerator has x squared and the denominator has a single x, they are by 1 apart. So when we do the long division over here, right, we will be able to find that asymptote. So x into x goes x times, multiply it back, x squared minus 3x, subtract it, these are gone, it's a 4x minus 6, x goes into 4x plus 4. That's it. As soon as you get the first two terms, we don't care about the remainder, you don't have to multiply it back, you just stop right away. Y equal x plus 4. That is your slant asymptote. So we have the horizontal asymptote, slant asymptote. And now we can graph and see if we need to do the point analysis or not. Vertical asymptote at 3. I like to use red for all vertical asymptotes. And then we have slant asymptote, that's orange. 1, 2, 3, 4. Y-intercept is 4 for that asymptote. And then I need a 45-degree angle here. Maybe I should move this asymptote somewhere else so it's not hitting the graph. So 45-degree slant asymptote. Then you have your vertical asymptote, right, at 3. It creates this wedge. Graph could be there, right? So I just need to make sure that I have access to all of this. Here is my y equals x plus 4. Slant asymptote, SA. All right. I also have some x and y intercepts. So y-intercept is 2. Graph has to go through this value. And I have some x-intercepts, -3 and 2. 2 and -3. I think one of these is obvious, right? Connect the dots from your coloring book, right? You will follow the slant asymptote into 3. You will bend at 4, go through 2, and follow the vertical asymptote. That one is common sense. Now, is it going to go up and then curve, or is it going to go? Yeah, that's going to be calculus, okay? Because we are going to deal with the greater details when we do the calculus list. Instead of having 6 of these, it's going to have 13 of these calculations. So much better time, right? Better party when you buy those tickets. Yeah. Now, look at the red line. We are done to the left of the red line because you cannot have a green, right? You cannot have that because it will fail vertical line test. Now, what do we have? We have the possibility to have a graph here and to have the graph on top. Now, I get to delete one of these. Come on. Which one do I get to delete? And why?
The bottom one because of the x-intercept.
Beautiful. No x-intercept here, so I have to get rid of this one, which means that the top one is the one that I get to keep, even though I don't have a lot of the, other information. There we go. And that's the graph. So now you can go and take the original graph, plug it into a graphing utility, and verify that this is it. So that's graphing rational functions. I know it's a lot, but one step at a time, small chunks. So if you have issues with this and problems, right, talk to me, see me during office hours, or ask next class, or during the review. We can do more of these, right? As you can see, you don't always have to do the number analysis at the end. Sometimes you do it like halfway. Sometimes you can argue these x-intercepts are not there, so you can eliminate the lines. The only thing you are not allowed, again, you are not allowed to stack up the lines in the same x-interval. So you cannot have the line here and on top to fail vertical line test. It's not a function, right? So its line is either up or it's down. And clearly, if it can't be down because there is no x-intercept, then it has to be up. All right, I'll see you later. Bye.